Hello, it's Dr. Daystorms, and in this section, we're going to go over electron configuration, and this is also going to be where we can use the periodic table to determine what's called the valence electrons, the ones that live in the outermost energy level, or outermost shell, and also it's going to really tie together some of the things that we've been discussing in this chapter, and really carry over to the next chapter when we start talking about properties of atoms. So, an electron configuration is just a way to write out the distribution of the electrons. Okay, so it consists of three things, at least. First, there's a large number that denotes what energy level that the electron resides. Secondly, we have a lowercase letter that tells the type of the orbital. Remember, that's the one that tells you the shape. And then finally, we say the number of the electron that is in there. And that's done with the superscript. And so for a P, you can have anywhere from P1 through P6. So this is an orbital diagram, and each box represents one orbital. And if you remember, if you look at the periodic table, lithium has an atomic number of 3, which means it has 3 protons, and it has 3 electrons for it to be neutral. And so I actually prefer, I like to write it this way because it shows the relative energy. We have lithium, there's the 1s orbital, so we have 1 electron, 2 electrons. Then we have the 2s orbital, which only has 1 electron in it. And we do these little single barbed arrows to denote an electron. And this way, it also clearly shows that the 2s energy level is higher in energy than the 1s energy level. So each half arrow represents the electron, or an electron, I should say. Well, what happens if we have something that's got more than 4 electrons? So let's just do an example here. Let's say, for example, let's do carbon. What's the atomic number on the periodic table of carbon? So let's first look at carbon. We've got to find its atomic number. And when we do that, we see here's carbon. And it's got an atomic number of 6. So that means it's going to have 6 electrons in the neutral atom. So let's go back now to our carbon. So we have carbon, and we have 6 electrons. Each electron has to have, remember, each electron, no 2 electrons can be the same. And so I'm going to write the C. We have a 1s orbital. There's 1 electron, 2 electrons. We now have a 2s orbital. That's 3, 4 electrons. And then we can have the 2p orbitals. And when I say 2p, there's actually 3 of them. Remember, we can have a px, a py, and a pz dumbbell. But we only have 2 electrons left. And so you may think, oh, well, we put, if this is the px, this is py, and that one's pz. You think, oh, we can just put 5 and 6, right? And you can fill up that hotel room if you want to think of it as a hotel room. I want to point out a couple of things. First, please note that the 2p orbitals are slightly higher in energy than the 2s orbital. Secondly, I want to point out that the 3 orbitals that are 2p's, like 2px, 2py, and 2pz, are degenerate. Remember, that means they're equal in energy. But finally, I want to say that that's incorrect in the sense that what happens instead is we want to maximize the number of the p orbitals that we use. And so we actually fill up all of the orbitals individually before we start doubling up with electrons. So that's the reason why instead we have 1 electron, 2 electrons, 3 and 4 go fill up to 2s, but then we have 5 and we have 6. We still have a vacancy here in the PZ. You want to try to maximize the number of hotel rooms, if you want to think of it that way, or orbitals that are degenerate with each other. That's called Hunds Rule. So what Hunds Rule states is that for degenerate orbitals, the lowest energy is attained when the number of electrons within the same spin is maximized. So what does that mean? They've actually shown you, this is for oxygen. And the reason why I know that is, look, there's 2 electrons, 2 more makes 4, 5, 6, 7, and 8. And so if we go back to the periodic table, we'd see that the oxygen is the one that has the atomic number of 8. Now, I like to show the energy levels actually being different in energy. You can clearly see that the 2s would be higher in energy than 1s, and 2p would be a little higher than 2s. So let's do another example of filling out the energy orbitals. Let's see. Let's pick, why don't we go with whoops, let's go back. Let's go with phosphorus. So, first of all, we find phosphorus on the periodic table, and it's got an atomic number of 15. So that means that there must be 15 electrons in the neutral atom. So we're going to have to find a way to put in 15 electrons in an energy diagram. Okay. So we have phosphorus, and it has 15. We're going to start with the 1s. There's here. There's 1s, we'll say 2s. We have 2px, 2py, and 2pz. We'll have 3s, 3px, 3py, and 3pz. Now let's start putting in the electrons. We fill up the lowest one first. That uses up 2. There's number 3 and number 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and even though you want to put 14 right there, that would be wrong. So it would be 13, 14, 15. We fill up all 3 of these degenerate ones, so that way we've maximized the total number of hotel rooms, if you want to think of the orbitals that way. And I want to point out that you never ever put more than 2 per hotel room. So notice down here, there's only 2 for every p orbital. It may be a little crude, but just think of it this way, as you wouldn't want to take your mother-in-law along with you on your honeymoon, so there can be a maximum of only 2 electrons for that hotel room. Okay, one with a plus 1/2 spin and one with a minus 1/2 spin. Now I want to show you something else. This gets a little cumbersome when we write it all out and draw it out like this. There's another way that we can do it. Actually, there's a couple of ways. One other way to do this, rather than drawing out all the energy levels, is that they write out the electron configuration like this. 1s2, 2s2, 2p6, 3s2, 3p3. Oops. 3. Okay? And if you add up all of the superscripts, they should add up to the total number that you have. So we have 2 plus 2 plus 6 plus 2 plus 3, which would be 15. And that's the number of electrons that phosphorus has. That gets a little cumbersome as well. So for example, if we go back to our periodic table, and we look something at like, oh, let's see, for example, barium, it would have 56 electrons, or it does have 56 electrons, so we would have to write out all of those electrons, all those energy levels and stuff, and so it makes it very, very difficult. So instead, there's another way to look at it. What would happen, or what happens, is if you go up one row, and we look at so it's this row right here, if we look at the noble gas that's at the end of that row, so if you look at the noble gas at the end of that row, which is xenon, barium was going to have the same electron configuration as xenon, except it's got two extra electrons. So what we can do, one way that we can write this, let's say that we want to do bariums, but we don't have to write out all of those numbers. We just say barium was equal to the same thing as xenon, because xenon is up one row above, and that's a noble gas, plus whatever's left over, which is 1, 2, 3, 4, 5, 6. It's in row 6, so it's going to be 6s2. So that's another way to write out the electron configuration. So we always fill our energy orbitals in order of the increasing order of energy. And in case you haven't caught on yet, but one interesting thing is the principal quantum number, which tells you what energy level it is, it also equals what row on the periodic table that element is in. So n equals 1 for hydrogen and helium. Then we have n equals 2, 3, 4, 5, 6, and 7. So that's why francium, which is way down there in the lower left-hand corner, it would have n equals 7. So by just knowing what row of the periodic table that your element is on, it lets you know the outermost energy level. Okay? Now, one thing I want to point out is I want to remind you that we have what's called the lanthanides and the actinides, and they are actually inserted here between 6 and 7 by the transition metals. I want to also point out now that if you look, the last electrons for anything in those columns are in the S, except for helium. Helium is an outlier. And then the last electrons for all of these are in the P's. These are all in the D's, and then the lanthanides and actinides are in the F suborbitals. I should say F subshells. So different blocks on the periodic table corresponds to different types of orbitals. So that's why you can get a lot of information from the periodic table. So let's blow this up. So anything in order here, it's that first column, its electron configuration is going to end with an S1. Anything in this column, its electron configuration is going to end in S2. This one would be a P1, P2, P3, P4, P5, and P6. Now the one exception is helium, which is 1s2 because it only has 2 electrons. But now if you notice here, what may throw you for a loop is notice the transition metals. They end in D's, but it's one row below. See, we have 4s2, 4s1 and 4s2. Then we come in and we have 3d1. So what's up with that? That's where some of the energy levels on the lower principal quantum number shell is actually higher in energy than the s orbital, okay? Which makes it a little difficult. Let me go back and I'll show you what I mean on that one energy diagram. So this picture was given in the last presentation, but I wanted to point something out here. We see where we have the 1s orbital, higher in energy is 2s, a little higher is 2p, then we go to 3s and 3p, but if you notice, the next energy level that's just up in energy is not 3D. Instead, it's the 4s. It's actually a little easier to put the electrons into the 4s energy level orbital than in the 3D orbital. And that's because, if we think about it, let me change the color. It's because you're going to have up to 10 electrons, and so they're going to be higher in energy because they're going to be repulsing each other just a little bit more than just the 2 that's going to be in 4s. So how is there a way in order for us to try to figure out the order in which you need to fill the energy levels from lowest to highest? And there is. It's called the Aufbau Diagram. So I'm going to attempt to draw this on here. The way that I learned it is you first just write out, there's the 1s, 2s, and 2p, because that's as high as it can go. But on the third energy level, it can go 3s, 3p, and 3d, because of the number of options with respect to the m sub l, angular momentum quantum number. I'm sorry, the magnetic spin quantum number. No, I'm sorry, I messed it up again. Magnetic quantum number. I'll get it right. It's m sub l. 4s, 4p, 4d, and 4 can go all the way up to f. And the reason why is, let's just review that real quick. If n equals 1, then L had to equal 0. Because remember, n, we had L, and L had to be between n minus 1 and 0. M sub L could be from negative L, to positive L. This is the one that tells you how many possible subshells are in each of the letters. The L value is the one that tells you how many letters there are. And so when n equals 1, L can only equal 0. So therefore there's only one possible. When n equals 2, L can equal 0 or 1. So this could be the 0, and that would be the 1. That's a 0. When n equals 3, it could be a 0, a 1, or a 2. And when n equals 4, it could be a 0, 1, 2, or 3. When n equals 5, it could be 0, 1, 2, 3, or 4. Go on and on and on. Let me take those off. Okay, let's go back here. So then we have 5s, 5p, that 5 didn't come out right, 5d, 5f, 6s, 6p, 6d, 6f. Yes, in theory you could have another 5 and 2 more 6s, 7s, so on and so forth. 7p. Hopefully you're getting an idea. Now, according to the Aufbau, actually I'm going to do this one. You make these diagonal arrows. Okay. So, if we look at this first diagonal arrow, it passes through 1s. The next one passes through 2s. Whoops. Then comes 2p and 3s. 2p, 3s. Then goes 3p, 4s. 3p, 4s. But now when we start back here, it's 3d. I'm going to have to continue this down here. 3d. And then I'm going to have to continue on the lower line. The next one is 4p, 5s. 4p, 5s. So if we go on and continue, we have 4d and 5p, 6s. 4d, 5p, 6s, 4f, 5d, 6p, 7s. So the order then, if I continue on, would be 4d, 5p, oh, I'm sorry, I'm looking at the wrong line. It's going to be 4f, 5d, 6p, 7s, and then you continue on. If we kept up with this, it would go 5f, 6d, 7p, 8s would be the next one, so on and so forth. That's the order in which the energy levels need to be filled. So if we look back at the periodic table, let's look back at this periodic table, and we can actually see that happening. We have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, then it skips down here to 4f, 5d, 6p, 7s, 5f, 6d, 7p. So you can see that's the order, that's the Aufbau diagram. So that tells you the order that the electrons, the valence shell electrons, the outermost shell of electrons, goes through. So let's just do an example based off of the periodic table. So if we look here, and let's do, it doesn't really matter which one we pick, but let's say that we do zirconium, which is 40. So zirconium equals 40. So I'm going to try to write it right here at the top. So we have zirconium. And if we want to write it all out long ways, well, first, let's write it out the quick and easy way. So what you do is, we are in row 1, 2, 3, 4, 5. So you go down to row 4. 1, 2, 3, 4. That's the noble gases krypton. So in square brackets, you'd write krypton. Then we would just start filling in the electrons after krypton. So we'd have 5, 1, 2, 3, 4, 5, 5s2, and then zirconium is 1, 2 over, so that's a 4d2. So that's the quicker and much easier way. Or if you wanted to write it all the way out, or if you're asked to write it all the way out longhand, zirconium would be equal to 1s2. Here, let's erase some of this so that way we can see what we're doing. Okay, so 1s2, that gets us through helium. 2s2, so now we've done those two. Oh, whoops. Okay, 2s2, 2p6, 3s2, gets rid of those two. Whoops. Trying to go back and forth between pens is difficult. 3p6 would get us through these 6. Okay. Then we actually hit potassium and calcium next, which would be 4s2. We have these 10 transition metals, which remember, the d orbital, those are the d orbitals, and they can hold, there's 5 of them, and they can hold 2 each, so therefore it's going to be 3d10. We've got 4p6. Whoops, if I switch. We have 5s2 to get rid of those two. And then we have 1, 2 more until we get to zirconium. So that'd be 4, because remember it's one lower, 4d2. So that's the longhand form of the electron configuration. Unfortunately, there are some anomalies. What happens is, if we look at the periodic table in the transition elements, what you would do is you would actually find a time when it's actually better to have enough electrons to half fill your S and half fill a D. So what do I mean by that? Let's look at, for example, let's see, 1, 2, 3, 4, chromium. Alright, so chromium, let's go back to the periodic table and I'll show you what chromium looks like. Chromium is right here. So its number is 24. There are 24 electrons in neutral chromium. So we're going to do the short method, the shorthand method. So we just go one row up and look at that noble gas. So it's going to have the same electron configuration as argon. So in square brackets we put argon. And this is what you would expect. Then we would have 4s1 and 4s2, right, to get rid of through to calcium. And then we would just have 1, 2, 3, and 4. So you would expect it to be, 3d4. So if we draw I'm just going to draw those last two energy levels. This is the 4s energy level. And then we would have 1, 2, 3, 4, 5 possible 3D energy levels. Remember, there's 5. And we'd have 1, 2, 3, 4. There's a problem here. We have this empty hotel room. So it's actually better for us to take one of these electrons and pop it into this one. So in reality, I'm going to show you what it looks like in a new slide. So what it really looks like is this. For chromium, it does look like argon, and then it has only one electron in the 4s orbital, and in the 5 3d orbitals, it has 1, 2, 3, 4, 5. It's actually better to have 2 half-filled orbitals that are completely full than it would be to have it look like to have it look like what I had up here, where we have an empty hotel room, an empty 3D orbital. This is better, and so we see that those anomalies in the transition elements. So to reiterate this, what's happening is there are irregularities occur when we have enough electrons to half fill the s and half fill the d orbitals on any given row. So this happens the most when we're talking about the transition metals, and also within the lanthanides and the actinides. Okay, so that's why chromium looks like, So that's why chromium looks like 4s1 3d5, because those two energy levels are really close, and it's just much easier and much better to have all of them half-filled than to have some of them fully filled and some of them half-filled and then one empty one. And so these anomalies also occur in those F-block atoms. Those are the lanthanides and the actinides as well. So let's go ahead and do some examples. I'm sorry if that was a little choppy in the video right now because my computer crashed. Oh, gotta love technology. But let's do examples. For example, let's go and let's work on, let's say zinc. So zinc has 30 electrons. Okay. Okay, so we said we're going to work on zinc. And we're going to do the shorthand method. Zinc has 30. There's the 30. So we go up a row and we look. So it's going to look just like argon. Except now it's going to have 4s1 and 2. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d10. So that's zinc. What if we do copper? Copper is another one of these that's an exception. Okay, so the reason why is copper's got 29. It also looks like argon. And so you would expect it to be 4s2 3d9. However, that the energy levels between 4s and 3d are so close together that it's actually better for it to be half filled here and totally filled in the d. What does that mean, or what does that look like when everything is said and done? Is instead of being 4s2 3d9, it's going to be half filled in the 4s, so it's going to be 4s1 3d10. So when should you expect some of these anomalies? Through here, these copper, silver, gold, they actually are better to have a half-filled S1 and a fully filled 3d10. And then I would expect you to also know that the ones right here that you would expect to be for, like the S2 D4s, are actually S1s D5s, because it's better to have them all half-filled. There are some anomalies here in the lanthanides where you can have some of the S's and the D's that actually get filled first before some of the F's, but I wouldn't have you memorize those. Just know that there are some anomalies down there. But I do want you to know these anomalies here, the ones where they are better to be half-filled, or the ones where the S is half-filled and the D is completely filled. Let's just work some more examples. Let's do, let's see, why don't we do tungsten? Tungsten is 74. Oh, whoops. Oh. Okay, let's do tungsten. So tungsten is 74. First off, it's right here. So we go up a row. Is that noble gas, and so it looks like xenon. Whoops, let me change back to the pen. So in square brackets we put xenon. Then we just have to put how it's different than xenon. So the way that's different is it's going to have 1, 2, 3, 4, 5, 6. It's in the sixth row. So it's going to have 6s2, because the 6s2 gets rid of these two. Then we got to cover all 14 of these. Those are the F orbitals or subshells. And so, therefore, that's the 4F14. Because xenon doesn't have those electrons. And then it's going to have 1, 2, 3, 4. 5d4. Now this isn't like chromium and molybdenum. It does keep it with the 5d4s. And one of the reasons why, or one way that you can think about it, is the fact that it's not going to take one from the S, because there's a whole full 4f14 in between the 6s2 and the 5d4. Okay, let's do another example. This time, why don't we pick antimony or antimony? I've heard it pronounced both ways. So that's SB. And it has 51 electrons. So you go up a row, and it's going to look most like krypton. So you do krypton. And then just the way that it's different than krypton. So we are going to have 1, 2, 3, 4, 5. So it's going to be 5s2 to get rid of those two. 4d10 to get rid of those 10. And then we have 1, 2, 3. So it's going to be 5p3. We can also work backwards. Why don't we do one where we work backwards? Okay, in this instance, or this example, you're given neon 3s2, 3p4, and you have to figure out what element it is. Okay, so first let's find neon. There's neon. So it means it has to be on this row 3. We get rid of 3s2, and we go 3p1, p2, p3, and p4 is right there. So that is equal to sulfur. Hopefully this has helped explain some of the way to do electron configurations. So let's just do a quick review. So first off, remember we do have 4 quantum numbers that describe the house or the address or social security number, if you want to think of it that way, of each electron. The N energy level, it tells what the N is the principal quantum number, and it tells the energy level that the electron orbital is on. The L tells the shape of the orbital or the house, if you want to think of it that way, and its angular momentum. The magnetic quantum number tells you the orientation, and then the spin tells you either plus 1/2 or minus 1/2. You can actually use the periodic table to determine the electron configuration. That's what we've been doing for the last several minutes. And finally, for a few atoms, it's better to have 2 half-filled subshells like S and P than to have a full S and a partially filled P. And so the ones to be on the lookout are things like, chromium, copper, where it's a half-filled S and a fully filled D orbital. Okay? And so it just takes some practice, and you should do as many example problems as possible in order to become more fluent in the way that this kind of vernacular is used. And I will see you in class.